Hello, everyone. My name is Juan Steibel. I am an associate professor in the departments of animal science and fisheries and wildlife at Michigan State University. My, my main research interest is in the area of quantitative genetics and genomics, specifically applied to pig breeding. But through that interest, I've recently been working on precision livestock farming and especially collaborating and interacting with colleagues that have precision livestock farming as their main area of work and research. Many of them, if not all of them, have been presenters today in the sessions. And so I will be offering a presentation on the added value of precision livestock farming data sets and also making a summary of the presentations. In the talks that we listened to today, we saw that precision livestock farming system usually record data from multiple sensors. And then those sensors could be, for example, wearable sensors such as RFIDs or accelerometers. They could be remote sensors such as microphones and cameras. But whatever those sensors are, the amount of raw data that they collect, it's usually enormous. And it's virtually impossible to store all the raw data and keep it. And so the solutions that are proposed, that were proposed today, was to analyze those data on the fly, real time, using automatic algorithms, and produce what I call usable or process data, which are simpler summaries, usually in the form of flags or indicators that can be used by the animal caretaker or the farmer to implement management decisions on the fly at real time. And from the presentations today, I think now we have a very good idea of what is the value in using the data in that way. But also, what I want to call your attention to today is the fact that an enormous amount of data is actually not used, and it has to be deleted. Even the process data, the flags, the management flags, sometimes are not kept because there is no reason for that once the management decision was made, and those have to be discarded. If we were to keep all of them for no reason, we would quickly run into storage problems and other issues for nothing, basically. So what I want to talk about today is what are the possible uses for the raw and the process data that is generated by precision livestock farming systems that would have an added value beyond and above any management decision that was already made using them. Before going into those specific uses, or some of those, I want to discuss or introduce this idea of the novelty behind the data recorded using precision livestock farming systems. From many of the presentations today, we observe that now we have the potential of recording novel traits that were or are extremely hard to record using the classic technology. And for instance, today we saw the case of monitoring pig feeding behavior using RFID tags or using computer vision. Similar idea also was presented for monitoring the feeding behavior of cattle. And also a very innovative idea was presented using sound recordings to monitor the feeding behavior of poultry. So feeding behavior in this case, that is directly correlated, as was shown in the presentations throughout the day, to a feed intake, and then that also relates to feed conversion efficiency. Those are traits that are extremely hard to measure, and they are usually not recorded in commercial farms. Well, now with precision livestock farming systems, we have the opportunity to collect those. But also, in addition to those novel traits, we also saw that these precision livestock farming systems are able to collect data from, I would say, classical or common traits that are routinely measured in farms, such as, for instance, weight gains and things like that. But they can be collected in a high throughput way. So they can be collected in real time in a continuous manner. For instance, we can use images. We saw the presentation of using images from pigs and from cattle to estimate the live weight. Now, instead of having to walk the animal to a scale, every time we want to measure the weight, the live weight, we can just take a picture or wait for the animal to cross in front of a camera. The camera automatically takes a picture and records that. And it can do that on a continuous basis. And now we have a classical trait that is recorded in a massive number of animals under normal production conditions and in commercial farms. Then today I want to talk about possible uses of this data collected in this manner, whether it's novel data or is data that we are already collecting, but now collected in an automatic and high throughput way. In which areas of livestock production system we could use them beyond the intended use of these data sets, which is for making management decisions. So I will be talking about incorporating those data sets into genetic evaluations, into welfare assessment, and on-farm research or on-farm product testing. Let's take a look on each one of those. In this slide, I'm presenting a timeline since the time a bull calf is born until the time that the first crop of his daughters have finished closed lactation. And by this timeline of around 58 months, now we have enough information to reliably evaluate the genetic merit of the bull calf. Now, as you can imagine, and many of you already know because probably you work with this, this is a very lengthy process, is time-consuming, is expensive, is justified because the value of the animal that is subject to the selection decision is a very large value. So the idea now is that, of course, with precision livestock, we won't be able to change this timeline. We won't be able to shorten it. But what we can do now is to start to incorporate traits and measure the traits that go into this genetic evaluation using sensors or using data collected from sensors used in precision livestock farming. In particular, to the classical traits that we are using right now in dairy genetic evaluations, such as milk yield, component yield, and type traits. We could also incorporate other traits such as feed efficiency, feeding behavior, etc. And moreover, we could measure the classical traits in a more automated way and in a very large number of animals. In addition to that, what I find that this is very promising for animal breeding and for animal breeders is the fact that now we can collect these phenotypes in an automated way in commercial animals. We are not restricted in working with elite animals, or for example, in the case of pig breeding in nucleus farms. Now we can go to production farms and start collecting this data in the actual environment in which the bull or the sire's genotype will be expressed in the progeny, which is the commercial animals. Today, for example, Dr. Doria from University of Wisconsin-Madison mentioned the key word that goes into this scheme from PLF into animal breeding, which is the word called phenotyping. Phenotyping is the measurement of classic and novel phenotypes or traits or variables in massive number of animals using automated technology. And that phenotyping can be done, for example, with some of the existing PLF technologies, provided that we keep some of those data streams and we link them appropriately. In fact, in order to get more relevant index of selections for the more relevant index of selection for the candidates of selection, in this case of this slide would be a bull, what we need to do is to link the phenotypes that were collected automatically on these commercial animals back to the genotype of the animal subject to selection. Also, Dr. Doria mentioned the idea and the need for individual animal identification. As long as we can identify and automatically identify animals in the commercial environment and attach a phenotypic measure to them, then we can propagate that measure back into the pedigree or the genome information that we have in the genetic evaluations and link that to the genetic merit of a candidate for selection. If that is challenging to do with images and with computer vision, perhaps we can consider the use of RFID tags that was presented by Dr. Brown-Brandel for pigs and for monitoring, for example, pig behavior and pig feeding behavior in particular. So regardless of how we do this, the key word here would be collecting massive number of phenotypes in commercial animals and then being able to link those to the lead animals being evaluated. Another area where PLF, precision livestock farming data streams could be used is in the area of welfare assessment. Currently, we have procedures for on-farm welfare assessment, which in general consists of looking at or observing certain variables and indicators on either groups of animals or on a limited number of individual animals that are not identified per se, but they are considered representative of the farm in which they are being raised. And of course, this is carried out in general by judges, which are experts and are well-trained for doing this, so they can add their subjective criteria and assessment to these objective measurements and come up with a scoring system. And there is no doubt and no question about this, because through using this type of on-farm welfare assessment, we've seen enormous improvement in the welfare of livestock and also in the societal acceptance of the animal products that we are selling. However, with the adoption of precision livestock farming, we would be able to automate the collection of those measurements that are needed for the welfare assessment. We would be able to do this on a more continuous way. And what is interesting, and perhaps is more interesting to our consumers, the people who will be buying these animal products, is the fact that we are not limited to observing a set of animals which have to be accepted as representative of the rest. We could do this on every single animal. And then, as we need, we can compute summary records for a certain herd or for a certain farm. For instance, in the presentations that we saw today, we saw that a common interest for PLF applied in pigs, in cattle, and even in poultry was to monitor behavior. If we can automatically collect a massive number of behavioral records, and then experts who analyze those and come up with what is called like a quote-unquote normal behavior, then by monitoring the individual behavior of animals, we could see abnormal behaviors and use those as indicator of welfare. Dr. Sigford, for example, Dr. Janice Sigford, who presented earlier today, is one of those experts from the animal welfare and behavior area that is currently working on designing welfare assessment schemes using precision livestock farming data. So this is a very promising area. And what I find promising about this area is the fact that will require that we connect the consumers associations with producers associations, and we link them with the experts in the precision livestock farming, in the welfare assessment as well, so that together they can come up with the indicators that will be collected and transmitted from farm to consumers and used for maybe perhaps create differentiated products which are welfare certified, or for establishing new industry standards in terms of welfare that will be not only easily adopted, but also easily evaluated by the farmer, and the farmer could adjust those on the fly as they are producing these animal products. And the final thing I want to talk about is this idea of using precision livestock farming data sets for research, for testing products on farm. As many of you know, we traditional researchers are used to work with a control environment, whether that is a laboratory or maybe an experimental farm. We usually have a very limited sample size in terms of animals, very limited number of locations. Maybe it's just one farm, maybe it's only a few experimental farms, a small network of experimental farms. And we allocate treatments or the products that we want to compare to these experimental units that are, in general, the experimental unit is either an animal, a single animal, or a small group of animals to which we apply each treatment. And then we measure all sorts of variables, and we measure the response, and we try to come up with answers to our research question. Of course, this experimental design is optimal for inferring cause and effect. For instance, we can design an experiment in our MSU farm, MSU dairy farm. We could apply different diets and then measure the response from those dairy cows or heifers, and assess if a change in diet is causing a change in feeding behavior, which in turn is causing a change in performance, in milk yield, or whatever measure of performance you want to use. What this type of experimental design is usually not very good for is for measuring the actual effects in commercial farms. So we can determine if a change in diet causes a change in performance, but it's hard to determine exactly how much it will change in a commercial farm by looking at data from an experimental farm. The environment is controlled, it's not similar to the, it's not exactly identical to those of commercial farms, and the number of animals is very used, is very small. On the other side, as precision livestock farming is adopted, I would say worldwide, but maybe we can think of the US in our case, and it's adopted by many farms. If we are able to capture these data streams, the desired performance variable that we want to study, we could compare treatments applied at the whole farm level. In this case, the farm would become the experimental unit. So one farm applies one treatment, another farm applies another treatment. But, and of course, there will be a lot of confounding factors. There will be many things that are changed from farm to farm. But the fact that we can potentially treat each farm as an experimental unit and measure the response in thousands and thousands of farms, that would, in and of itself, provide a very good estimate of the average effect of the treatment. Now, maybe this is not good for inferring cause and effect. That still will have to be done under some control environment. But once we know that there is an effect, to estimate the size of the effect, this will be much more effective than trying to, let's say, run experiments in an experimental farm. For example, an interesting problem that we observed, that we saw today in the presentations, was by Dr. Tammy Brown Brandl, and she used precision livestock farming technologies to assess the effect of heating element, the position of a heating element in farrowing crates, and how the animals responded to that, and to make decisions about the placement of those elements. Imagine if we could repeat this in thousands of farms. If this was a technology that was already adopted for management decisions within the farm, we could collect the data from thousands of farms, and not only collect the data on the heating element position, we could collect data, for example, on the type of heating element, the design, the brand, the characteristics, and maybe electricity consumption, things like that. Then we would be able to analyze all those data and group these farms into common practices and into common types of management regarding that particular heating element, and come up with a solution to increase the energy efficiency of farrowing rooms across the whole country. Perhaps we cannot narrow it down to a single configuration, treatment configuration that will be the best over all the farms, but we can narrow it down to a few options, and then within farm testing, using the same PLF, will help the farmer decide exactly what to do and which type of elements use. So this is just an example. It's more daydreaming on part, but it's just to show you the idea of how using data that's already collected for making a management decision within farm and linking it across farms let's say from all over the US, we could come up with new technological solutions for management. So comparing treatments at the broad level of region or country. And the key, of course, the key for this to work is that we need to be able to access all the data. We need to be able to link the data records from each farm to other data sets which are collected on farm and off farm, and that will help us build the statistical models to dissect all these effects. In summary, I hope that by now I was able to convince you that there is value in extracting these data sets and using it for something other than making immediate management decisions. But what is most important, the most important message I want to convey is that for that to happen, for that value to be realized, we need to extract selected data and transmit it through the cloud so it can be reused. And Thomas Norton gave a presentation today where he mentioned that this is already being done by experts in precision livestock farming. So I hope that we can build on that and use the data for other purposes. In summary, for this field to move forward and for these ideas to move forward, I envision three big needs. One is an increased infrastructure for information technology for storage, transmission, and analysis. The other one is interdisciplinary input from engineers, from experts in genetics, in behavior, veterinarians, work together to realize this value. And finally, as it was mentioned by Janice Sigford, we will need to consider the social and legal consequences of sharing data that generates value. Who will own the data, how that sharing will be compensated, and so on and so forth. But with that, I want to thank everyone who attended this talk, and I'm available for answering questions.